Okay, good day class. All right, so last lesson we have learned series expansion of the sum, differences, product and quotient. All right. Then after that we also have discussed differentiation and integration of a power series, or how we use the standard Maclaurin series and also using the differentiation and integration. All right, to find the expansion of another function. So remember this part we only have 4 examples and we have discussed it. All right, so today we are continue to the last part. All right, 5.1.4 application of Maclaurin series. How we can apply Maclaurin series on our calculation in mathematics. All right, okay, so 5.1.4.1. so before we want to apply Maclaurin series, so we are going to see geometrical approximation by Maclaurin's polynomials. Means that how we can use this Maclaurin series to find the approximate values of two important fields. It is to find the approximate value for the definite integration and also to find the approximate value for the limits of a function. We apply these two. Okay, so before we apply, so we have to know how we say that Maclaurin series can approximate a polynomial. Okay, so you see the geometrical approximation to certain function by the first few terms of their Maclaurin series, we call it Maclaurin's polynomial, shown as below. So you see how we can compare them. All right, so you see this is the first one. Okay, let's say this is a function for ex, and this is a standard Maclaurin series for ex. All right, so you compare. If we take the first two terms, the first diagram, okay, this is function ex and this is the standard Maclaurin series for ex. Many terms, right? Okay, if we just take the first two terms, 1 plus x. So if first two term 1 plus x, you can see, I make it bigger. All right, okay, and I enlarge it a bit. Okay, so if you take the first two terms only means 1 plus x, so it's a straight line, right? Also it's like this, and this is the actual function for ex. Not that close lah. All right, okay, so look at the second one here. If we take the first three terms of the standard Maclaurin series, so first three term is 1 plus x plus 1 over factorial 2x squared. All right, so means that it become a quadratic function. All right, and now you compare. Okay, this is this one. This one is the quadratic function, 1 plus x plus 1 over factorial 2x squared, and this one is the actual function for ex. All right, so from here you can see actually it's quite close already, right? The first three terms of the Maclaurin series is quite close to the actual function of ex already. Okay, so this is first three terms. So how about if we take more terms? Look at this. See, yes, if we take more terms, so means we take the first four terms is 1 plus x plus 1 over factorial 2x squared plus 1 over factorial 3x cubed. So it's a cubic function. All right. So you see that this is the cubic function, and this one is the actual ex function. So you can see that from this part onwards is really very close to each other already, except here lah, except here. All right, this is why, remember when we find a standard Maclaurin series, we have to write the interval of convergency. Yeah, it means that when x takes certain value, then it's actually really close to the actual function already, right? So this is what that means. So for this one, if we take this one as the approximation, suppose the interval of the convergency will be something more than negative 1.5, because if more than negative 1.5 is actually very close to the actual function already. But if out of the function, out of 1.5 or out of negative 2, or negative 1.5 or negative 2, you see it go further, it go to another way, which is not converged to the actual function already. So now you understand the why we have to find the interval of the convergency. All right, it shows that in certain value the Maclaurin series that we use is very close to the actual function. All right. Okay. Then we see one more. If we use the first 5 terms, all right. So it's a quadratic function. First 5 terms. So you see, first 5 terms. Compare first 5 terms means the quadratic equation to the quadratic. Or you compare these two. This is quadratic. All right. This is quadrile. All right. So the shape of the quadrile function, this one, and the quadratic is actually quite close to each other. All right. But when you compare this part, this quadrile function is actually even closer to the actual value. And of course, again, we have the interval of convergence. You see, if less than 1.5, then yes, it can be used. But more than 1.5, then yeah, it is not converged anymore. It go to another direction already. Okay? So from these 4 diagrams, it show that, okay, from these 4 diagrams, it show that actually the Maclaurin series, or the Maclaurin expansion, can be used to find the approximation of a certain function. But of course, again, we have to have the interval of convergence. All right. Okay, so we see another example. This is for sine x. All right. The actual function is sine x. Okay, this is the standard Maclaurin series for sine x. All right. So let's see, we are using the first 2 terms. So first 2 terms is this 2 lah. So it's a cubic function. So this is the cubic function. This one. All right, here. This is a cubic function. All right. This one is the actual sine x graph. All right. So from here you can see in between negative 1.5 to almost 2. You see they are very close to each other. All right. How about if we take more terms? If we take the first 5 terms, all right, it becomes a polynomial with power 6. Power 9, degree 9. All right. So this is the function for degree 9, and this is the actual sign. You see that it's even closer to each other, and the interval of convergence even wider or bigger compared to when we only take 2 terms. Okay. So this is the meaning that we are using graph to show that actually we can use Maclaurin series, the expansion of Maclaurin series, to find the approximate value of certain function. All right. So you see, the conclusion is, it is noted that when more terms of a series are used, the approximation become better, right? Each series tends to provide its best approximation when x is closer to 0. Of course, you see all the graph when closer and closer to 0. The expansion, the series, and the actual function almost overlap. Almost overlap means almost exactly the same. Even for ex also. Alright, you see? When x equals 0, they are almost like at the same point already. Means the smaller values of x you take, the closer the approximation is. Okay? Alright, now we see how we are going to apply. Alright, we see how we are going to apply this. So today we are going to discuss how we can use the Maclaurin series to find the estimate the value of a definite integral. All right, so we can use a Maclaurin series to estimate the value of a definite integral, and the values of x in the range from the lower limit to the upper limit of the integral must be small so that the term in x will be higher power can be neglected. All right, so means as we say just now, right? The smaller the x is, means even almost to 0. When x 0, they're almost the same value. Okay, therefore we are the limit in the definite integral is even smaller. Okay, so because this part we are involved a little bit of integration, and as we know, you already learned integration in Form 5, so there is not many extra techniques for integration. It's just a normal integration only. But anyway, we will discuss a few simple and basic technique of integration before we going on. So to do some revision, Okay, so we know that, let's say, if y equals x squared, all right, differentiate you have learned. Differentiate means dy dx. And we know that differentiate, index we put in front, you copy the base, then index minus 1, right? This is for differentiation. Okay, how about integration? I hope you still remember. If y equals x squared, when we want to integrate it, when we integrate x squared with respect to x, same lah. If differentiate, we differentiate y with respect to x. Integrate also the same. You integrate a function also with respect to x. Alright, so integration, still remember, integration is we copy the base, alright, index plus 1. Okay, differentiation, index minus 1, right? So for integration, index plus 1. Then over the new index. Over the new index. It's different compared to differentiation. But we also learn the concept that actually integration is the reverse of differentiation. Alright, this one later we will discuss. Okay? So I hope you remember these basic things about about integration. And remember, if it is a constant, if we differentiate a constant, it becomes 0. But if we integrate a constant, it becomes 2x. Alright, don't forget it. So this is indefinite integration. Indefinite integration means we don't have limits here. Okay? Indefinite integration. So we don't have limits here. Alright, no limits. So we have to write plus c. Still remember? Okay, but for you, by using the Maclaurin series, we are going to do definite integration. Means we have limits. This is what we mentioned in the notes just now. The upper limits and lower limits. Okay, of a function. It must be small. Okay, so that the approximate that we get will be better. Alright. Okay, now we can start. Alright, we will see how we can use this Maclaurin series to estimate the value of a definite integral. Okay, so before this, first we are going to see one example in your textbook first. Alright, and then we will discuss 2 questions here and the STPM question. Alright. Okay, so example 17 in your textbook, page 167, which is this one. Okay, we make it smaller. You can open your textbook also if you want. Yeah, okay. Alright, so this is the example. So using the first 3 non-zero terms of the series expansion for this function, okay, estimate the value of the integral of this. We want to find the Maclaurin series of this function, then we integrate them. This is the definite integration where you are given the limits. Alright, so first step, very simple, since it's involves sine x, sine x, right? Alright, so this is the standard Maclaurin series for sine x. Sine x squared means we square them. Remember we have discussed this before. Then we expand, because the question only wants the first 3 non-zero terms. Means up to power 6 lah. Other than power 6, when you expand the terms with higher power than 6, then you can ignore. Alright, so this is sine square x. Alright, so sine square x over x, just divide only. Just divide only. Divide all this by x. So you see all become like this. Okay, so this is the Maclaurin series or Maclaurin expansion for this function. Alright, so after we have the series already, we integrate both sides actually. You see, we integrate this one, we integrate this one. Of course, don't forget to write with respect to x. Okay, therefore this one is easier to integrate compared to this one, right? So remember just how we say integrate x, I have x squared over 2. Integrate x3, I have x power 4 over 4. So 3 times 4, 12. Alright, integrate x5, I get x power 6. Index plus 1 over new index. So 45 times 6, 135. Alright, this is the lower limit and upper limit. Then next step is we sub the upper limit first. Sub upper limit into the function. So like this, sub upper limit. Then suppose you have to minus. After you sub the upper limit, okay, you have to minus, you sub the lower limit. Okay, but you see each term also involve x. So when you sub 0 in, all becomes 0. So you can just write one time of 0. Okay, one thing that they didn't write here, please, you always have to write plus dot dot dot, plus dot dot dot. Okay, then the last step, yes, you put approximate sign. Alright, so the definite integral for this is approximate to 0.1310. This is what we are going to do later. Okay? Alright. Okay, next. Okay, we are going to discuss question 2. So by using the first 4 terms. Okay. Oh, the light's off. That's a bit dark. Okay, so by using the first 4 terms of the expansion of the integrand, estimate the values of the following definite integral. Oh, we just need the first 4 terms. Okay, so I'm going to discuss C. Alright, integrate x ex with respect to x from 0 to 0.02. Okay. Alright, this one. Okay. This is last lesson one. Okay. So example, question 2b. Okay, you can see. Yeah, can see. Okay. So question 2b. Find this one. Okay. So first we have to find the expansion for xex. Alright. So very simple. X just x. So the standard Maclaurin series for ex is this one. We want first 4 term. So until 1, 2, 3, 4. Then don't ever forget your plus dot dot dot. Okay. Then expand it. Multiply in. Expand it. And you get this thing. Alright. So once you get the standard Maclaurin series, okay, continue. Alright, so integrate both sides. So just put the integration sign on both sides with respect to x. Alright, so this is what we want to calculate. So you just have to do the right hand side. So integrate x, remember, x squared over 2. Integrate x squared, x power 3 over 3. Integrate x power 4, power 3, so index plus 1, 4 over 4. So 1 over 2 times another 4, 8. Okay? Then x power 4, so index plus 1, x power 5. So over 5. So 6 times 5, 30. Okay? Don't forget, again, plus dot dot dot. Alright? So the next step is sub in the limit. Okay? The next step is just sub in the limits. Okay? Sub in 0.02 into here. All this. Sub in 0.02. Okay? Then write minus 0 because later you have to sub in 0. But all the terms is with 0 with the x . So means all becomes 0 . Okay? Then we use a calculator to calculate. So remember the approximate sign. Alright, so if we use 4 decimal places, so the answer is 2.0269 times 10 to the power of negative 4. Sorry. You realize that I can't see. Okay, like this. So we sub in the upper limit 0.02 into the integrand. Alright, then minus 0. Because when you sub in the lower limit 0, everything becomes 0 . Then again, please don't forget your plus dot dot dot. Okay. Then the last step, only you use approximate sign. So it's approximate to 2.0269 times 10 to the power of negative 4. Alright? So not difficult. We just do something like this only . Where you find the expansion of this integrand. Alright, then you integrate both sides. So what you have to do is just you do the simple integration here. Okay, do the simple integration here. Then just sub in the upper and lower limit. Alright, and get the answer. It will be roughly like this . Okay, so the next question that we are going to discuss will be D. Alright, so for D, you are asking here. Can you see? Find the definite integral of 1 over square root 1 plus x squared dx from 0 to 0.1. Also, you see that all the limits given to you is very small. So first thing, we have to find the expansion for this function. Alright. Okay, so this one, rewrite it in this formula, 1 plus x squared. So square root is power half. So when we move up, it become power negative half. This one, we don't have to use the standard Maclaurin series lah. Okay, you can use the binomial expansion. Alright, binomial expansion. Just use binomial expansion. Or first term is 1 because here is 1. So first term 1. Second term, the index, multiply the first term. So now it's not x. Now your variable part is x squared. Then next term is index negative half, right? Then minus 1. So negative half minus 1, negative 3 over 2. Then 2 factorial. Okay, then your variable square. So your variable now is x squared, so another square. Alright, and the third term, same lah. Negative half, just now minus 1 is negative 3 over 2, minus another one, negative 5 over 2. And factorial 3. So this is factorial 3. And your variable cube. So your variable now is x squared, so x squared cube. Alright, so we just need the first 4 terms. Okay, then simplify them. 1 minus half x squared. This one x squared and square, so x power 4. This coefficient part, after you simplify, is positive 3 over 8. Alright, so this one x squared and cube again, so x power 6. So when you simplify the coefficient, so it's negative 15 over 48. Alright, negative 15, 48 actually can be simplified some more by 3 lah. Or simplified by 3. Okay. Alright, so next step, same like just now. Same. Oh, sorry, cannot see. Okay, now can see. Okay, now can see. Just now as I said, okay, we expand it up to the first 4 non-zero terms, then simplify. Then next step, integrate both sides. Integrate this one with respect to x, integrate this side with respect to x with your limits. Alright, so we just do integration to this part. Okay, so remember, integrate 1, you get x. Integrate this one, so it's x squared become x cubed over 3. So 2 times 3, 6. This one, x power 4, after integrate, become 5, over 5. Also 3 over 40. This one, x power 6 become x power 7. So this is 5. So 7 times 16, 112. Don't ever forget your plus dot dot dot. Okay? Later when you pass up your quiz, I don't want to see anyone forget the plus dot dot dot. Okay? Next step. Yeah, you sub in your upper limit first. Sub 0.1 into all the x, like this. This step must show, okay? Please show this step. Okay. Then minus, sub in your 0. So because all the terms are with x, even though all these terms with x, so we know everything become 0. Alright? Then now you use your calculator. Okay, to find the answer. Yeah, don't forget the approximate sign at the last step lah. So it's 0.09983. Okay. Not difficult, right? This part not difficult. Okay, now after that we are going to discuss one longer question, one STPM question. Alright, so we are going to discuss one STPM 2018 question. Can you see? Yeah. You see this question. So if y equals this one, show that dy dx is xy cubed. 2 marks. Actually, this part we have done. But never mind, later I will explain again. Then B, obtain the Maclaurin series for this function up to the terms in x power 4. 7 marks. Alright, so you see, first, they already asked you to find dy dx. Second, they give you 7 marks for this one. So it's definitely need to use Maclaurin's theorem, even though the question never say. Definitely you need to use Maclaurin's theorem, where you need to find your f0, f prime 0, f prime prime 0, and so on. If up to x power 4 means you have to find to the 4th derivative function. Alright, then use the Maclaurin's theorem formula to find the series. Alright. Okay, after you get the series, hence find the Maclaurin series for arc cos x. So maybe you will think, because of the word hence, right? So means we have to use this series to find arc cos. So maybe you'll think, what is the relation between these two? Never mind, later we will see, okay? So only 3 marks. And C, deduce the approximate value. So this is the part like what we have discussed here. This is the part. Another 3 marks. So in 2018, this is a question in part B, where it is 15 marks, you see. Okay, it's quite long, especially here. All right, because we have to differentiate until the fourth derivative function. Okay, we see slowly. All right. Okay, first step, like this. All right, I write it in this way lah, easier to differentiate. So the first derivative dy dx will be, so index in front, copy the base, index minus 1. So negative half minus 1, negative 3 over 2. Don't forget, multiply, differentiate whatever inside here. So differentiate this one, you get negative 2x. Alright, so 2 and 2 can be simplified. Okay, so we rearrange it in a nicer way. So it is negative, negative, positive. Or left one x outside only. Okay, then 1 minus x squared. Okay, this is negative 3 over 2. The power is negative 3 over 2. Why I want to separate it like this? Because the question wants us to show, right? This is the answer. It must be in terms of y. Alright, so y is like this. So therefore, I split this power into this way. Can, right? Same, So power and power means you multiply them. So negative half multiply 3, negative 3 over 2. Okay? So this is your y. This is your y. So become x, y cubed. This is the first part that they want you to show, which is only given you 2 marks. 1 mark here. 1 mark for your differentiation, of course. 1 mark for you to show this thing and write the answer. Okay? Don't straight away from here jump to your answer. You must at least show this step. Okay, so this is part A. Okay, next. After you have shown your dy dx, now we are going to do Maclaurin's theorem. We do like something revision. Okay? So just now we already said this is your y. Last time, can see? Okay, can see. Okay, so last time we are using fx, right? Then we will find f0. Okay, but now they give us in y. Of course, you can add one step and say let this is fx. Then you can use all this. Okay, or else we can just use y only. This is the way we can write. So this is y. So this is a value for y when x equals 0. Okay, or if you don't want, you can write this when x equals 0, y equals 1. Also can. Up to you how you want to write. Alright. So you see when you sub x equals 0 here, so the answer is 1. Okay, second step, dy dx. Okay, just now part A already calculate, right? So dy dx is xy cubed. Alright, so as I say, you actually can write like in this way. Dy dx when x equals 0, you can write in this way. Okay, if you don't want, you can just write like this. Okay, but not like this anymore. So when x 0, dy dx 0. Because x 0 so 0 multiply anything also 0. Okay, now next step. We have to differentiate this again to get the second derivative function. Alright? Okay, so second derivative function. So we know that we have to use product rule. Product rule. So this is your u, this is your v. Okay, product rule. So u dv dx. So differentiate y cubed. So 3y squared. Don't forget your dy dx. Because we differentiate y with respect to x, but here no x, right? So we have to add this term. We already learned why to do this already. Then u dv dx plus v. So copy your v du dx. So differentiate x, you get 1. Just like that. Just that simple. Okay, so I write it in a proper way. Okay, I write it in the proper way. So 3xy squared dy dx plus y cubed. Then sub in x equals 0. So very simple. X equals 0. This whole thing is 0. Right? And y cubed. What is y? Y is here. So when x 0, y is 1, right? So your d2y dx squared is 1. Just sub in like this. Okay. Now next. Next, which is a bit more complicated Okay, so to do the third derivative function is a bit longer. Have to be more careful. Okay, so we have to differentiate this term and also this term. Okay, So to differentiate this one, okay, to differentiate this one, I separate it like this is my u, this is my v. This is u, this is v. I'm using this. Alright? Okay. So we know that is u dv dx. U, copy the u, then dv dx. Differentiate this one. Okay? So to differentiate this one, I do separately here. Okay? To differentiate this part only, I do separately here. So differentiate y squared dy dx. So here also we use another product rule, another uv. Okay? So you see u dv dx. So differentiate dy dx, you get d2y dx squared. Alright? Plus v, so copy your v, and du dx. So differentiate y squared is 2y dy dx. 2y, don't forget your dy dx. Okay. So can I? Then we simplify them. So here y squared d2y dx squared. So here is 2y. So dy dx times dy dx is square of dy dx. Alright, so please write it correctly. Second derivative is d2y dx squared. This one different. This is square of dy dx. Okay, it's two different things. Don't confuse. Okay, so to differentiate this part, we get this. So I copy this one back here. Okay, so u dv dx, then v, so this one just copy, du dx. So differentiate 3x, just 3, right? Okay, so this is the part. Okay, this is the part to differentiate this one only. Then next, differentiate y cube. This one easier. Differentiate y cube is 3y squared dy dx. Alright? So next step, we just actually write it in a proper way only. So that we can differentiate next easier. Easier to differentiate the next one. Okay? So we just rearrange in a proper way. So 3x have to multiply inside here. So 3x y squared d2y dx squared. Then 3x have to multiply this one. So it's 6xy square of dy dx. Alright, so this is 3y squared dy dx. This is also 3y squared dy dx. So these two are similar terms. So 3 plus 3, 6. Okay? So this is a third derivative function. Okay, now we sub in x equals 0. So very simple. When x equals 0, this whole thing 0. When x equals 0, this whole thing also 0, right? So left this one. So we already know that when x equals 0, y is 1. Okay, but dy dx is 0. Refer back here. See? Okay, when x equals 0, dy dx is 0. So when you sub in here, dy dx 0. So when x equals 0, the whole third derivative function, 0. Okay? Alright, now next. Okay. Alright, so next, we are going to see how we are going to get the fourth derivative, which is more complicated. Okay, so before I go to it, I show separately first. Okay, so like this one, the first term, I will take this one as u, this one as my v. Okay, so I'm going to show you how to differentiate this term first. Here. Alright, then the second term also the same. I'm going to take this one as my u, so this one as my v. Also, I will also show you how to differentiate this separately first. Okay, this one no problem, this one quite simple. Okay, now we see. Can you see here? Okay. Alright, so now you see, differentiate this part only. Differentiate y squared d2y dx squared. Alright, so same. This is my u, this is my v. So u dv dx, so differentiate d squared, you get d cubed. Then plus v, so copy your v, du dx, differentiate y squared. So it's 2y, then dy dx. Now just simplify it. So it's y squared d cubed plus 2y dy dx, d2y dx squared. This is dy dx, this is d2y dx squared. It's separate. Okay, what else for this one? For this one. Alright, differentiate y square of dy dx. Okay, so also same. This is your u, this is your v. Okay, so differentiate, then u here lah. Put u here, differentiate this one. So same, differentiate this one is index in front, copy the base, index minus 1. Then don't forget, you have to differentiate inside, right? Yeah, you have to differentiate inside here. So differentiate inside here is d2y dx squared. Okay, then this is u dv dx. Then plus v, so copy your v, du dx. Differentiate y is 1 dy dx. Alright, so we write it in the proper way. So 2y dy dx, d square y dx squared. So this one is square of dy dx, multiply another dy dx, so it's cube of dy dx. It's quite long, this one. Alright, okay, now next step, we're going to sub back into here to get our fourth derivative function. Alright, so here, go back to this one, u, v, so u, copy, differentiate this one is this, so I just copy here. Alright, then v, this is v, copy, differentiate u, so differentiate 3x, 3. Okay, alright, so this is only for this term. Okay, now this term, also another uv. Okay, so u, 6x, dv dx, differentiate this part is here, right? So copy in. Alright, then v, copy v, differentiate 6x. So differentiate x is get 6. Alright, but don't forget, we have this one some more. We have this one some more. Okay, not enough space. So actually, I write it here again. Okay, so that you can see. So I just sub here already. I write it smaller so that you can see better. So this is the differentiation for first term is here. This one I copy here. This one I copy here. Alright? This one I copy here, and this is the last one. See? This is the last. This is the last one. This one. This one is for this term. Okay? So also UV lah. Hey, hold on. Oh no. This one's still here. Sorry. Here. Yep. This one. This one is for the first term. Differentiation for first term. This whole thing is the differentiation for this term. Alright? And the differentiation for this one is here. Okay? So same lah. This is my u. This is my v. U, v, So u, dv dx. So differentiate dy dx. You get d2y dx squared. Then v, copy your v. Differentiate 6y squared. So index in front, so 12y. Don't forget your dy dx. Okay? Alright? Okay. Do like this. Alright, so this is your fourth derivative function, which is really, really long. Okay? Then I rewrite it in a proper way lah, because 3x have to up to you lah, because this is the last step already. Alright, this is the last step already. Up to you, you want to rearrange in the proper way or not. Or you can straight away sub in x equals 0 already if you want. Alright, because this is the last step already. Before this, I have to rearrange in a nicer way so that easier for me to sub in, right? But yet I rearrange it in a nicer way lah, because 3x have to multiply in, right? Okay, so this one I write everything. 6x also have to multiply in. I write everything in a proper way lah. Okay, now we sub in when x equals 0. You can see, okay. Alright. So now we see when x equals 0, what is the value for d4y dx squared? X 0, so very simple. You see, here got x, so no more. Here also got x, finish, become 0. Here also got x, finish. Here also got x, finish. You see? All this term, no more. Okay, so all the terms with x become 0 already. And before this also we have done, when x equals 0, dy dx also 0. Okay, so sub all the dy dx become 0. Okay, so dy dx also 0. Where got dy? Here got dy dx. So this one also 0. Here also got dy dx. So here also becomes 0. See? So actually left 2 terms only. d2y, dx squared, and y. These 2 values also we have, right? When x equals 0, y is 1. And when x equals 0, d2y dx squared also 1. Alright? Y is 1, d2y dx squared also 1. So sub in here. So this is 1 times 3 is 3. This is also 1. So times 6 is 6. So 3 plus 6, 9. Okay. Right. Not easy, this one. Very complicated. Later I will put everything in a nicer way so that you can snap. Okay? We finish first. Okay, so after we got all the values, now, yes. Okay, we sub into the Maclaurin's theorem formula. I'm still using f prime lah, but you know that it's actually dy dx, d2y dx squared, d3y dx cubed, and d4y dx power 4. Okay, so sub in. So when f0 here, this one, here, f0 means this one, 1 no, huh? Okay, 1. Then f prime 0 just now we know is 0, x. So class, remember, if you don't want to write this step, okay, if you don't want to write this step, then at least you show sub 0 into the x. Or f prime 0 is 0. Write this one. Or don't immediately skip this step. If you don't want to write this one, this step must write. This step, as I told you before, this step is actually to remind you about the formula. Okay, to remind you about the formula. But this step also must write, subject with. And f prime 0 just now is 1, right? 1. Don't forget your factorial 2, you know. Because your last quiz, I saw that, your last quiz, many forget about this denominator. They just write all this numerator value only. Okay? So f prime 0 is 1. Means d2y dx squared. So factorial 2 is 2. Okay? And f prime 0, d3y dx cubed is 0. Sub 0 inside the formula. Don't straight away skip the step. Alright? Then fourth derivative is 9. 9 over factorial 4. So factorial 4 is 24. Okay? So the question want you to do up to x power 4. Then now only you simplify in the simplest form. So 1, now you can skip this one. Plus half x plus 3 over 4 x power 4 plus dot dot dot. Okay? This all this. Okay, now I write and make it in a proper way so that you can see the whole question. Let me see. Can you see or not? Up to this one. Okay, so this is the first step, second step, alright, which we have done in part A. Then after that, all this. Okay, you can snap, you can if you want. Alright. So this is only part B, 7 marks. Alright. Not yet finished. This is only part of part B. Alright, remember, part B, they want you to find the series for this function, and then the question, hence. This is until here 7 marks, yes. Hence is another 3 marks. Hence, find the Maclaurin series for arc cos x. How we are going to use this one to find the series for arc cot x. Alright? So the next step is, so I remove this one. Okay? So the next step is here. From the formula list. Now you check your formula list in exam. They actually give you this. When you differentiate arc cos, you get this one. Okay? So just copy from the formula list. Differentiate arc cos, I get this. Because the question wants us to find arc cos, so I choose this one. Alright? But when I see this thing, here no negative, but here got negative. Doesn't matter. Okay, before I carry on, I want to explain one thing that you have learned in Form 5 actually also, but I repeat again. Okay, so remember, when you have a function y, when you differentiate, you get dy dx, right? So when you get dy dx, when you integrate dy dx, you will get back your y. This is a concept. As we say, integration actually is the reverse of differentiation. Okay, so means when you integrate dy dx, you will get back your y. When you integrate dy dx, you will get back your y. So we are using this concept here. Okay, so this one, from the formula list, we know that differentiate arc cos x, we get this thing. So this is like our y this arc cos x is like our y here. Alright, then when I integrate both sides, so you see, I add the integration sign. When I integrate both sides, of course, with respect to x. Okay, so by using this concept, integrate dy dx, I get back my y. So this is my y. So integrate d arc cos x dx, I will get back my arc cos x. This is the left hand side. Okay, we are using this concept. So for this one, as I say, our expansion that we calculate here without the negative. So very simple. Again, you have learned in Form 5 also. The negative we can put outside the integration sign. Just put the negative outside. Alright? So now we are going to concentrate on this side, like what you have done. Okay, like what you have done. Okay, so the next step is here. Can see here? Alright, can see. Alright, so left hand side already get arc cos x. So left hand side we integrate this. So just now from here we already get the expansion. So just copy inside only. Don't forget your plus dot dot, please. No, don't forget. Okay, again negative put outside. So integrate x, integrate 1, you get x. Integrate x squared. So index plus 1, 3 over new index. 2 is still remain there. X power 4, index plus 1, x power 5 over new index. 3 and 8 are coefficient, just copy. Alright, then plus dot dot dot. Remember, this one is indefinite integration because no limits. No limits given here. Alright, so after you integrate, you have to plus c. Okay, plus c. Okay, now the minus we multiply in. Okay, multiply in. Just multiply in the negative and then plus c. Alright, then we are going to calculate what is this c. What is this c? So very simple. We know that when x equals 0, arc cos 0 is 90, right? Because cos 90 degree is 0. Cos 90 degree is 0. Okay, so arc cos 0 is 90, but we don't use 90 lah, we use pi over 2 lah. Always use radian. Okay, so sub these two values inside this integral. Okay, so left hand side arc cos 0 is pi over 2. Okay, right hand side all the x 0. Left the last one plus c. C is a constant. We call it integration constant. Okay, so all 0, so we get that c is actually pi over 2 lah. This one can be calculated. We will learn more. Actually, you have learned all this in Form 5 lah. Okay, we will learn again in Chapter 3 later. Alright, therefore, the expansion for arc cos x will be, because since all this negative, only the c is positive pi over 2, so I put it in front lah. Easier to see, nicer to see also. So pi over 2, minus. Don't forget again your plus dot dot dot. Then complete part B. Okay, complete part B. Okay, now we go to question C. Okay, so question C here. You're asking to deduce the approximate value for integrate arc cos x from 0 to 0.5. Okay, then your answer to 3 decimal places. 3 marks only. Okay, so the next step is like this. Okay. I remove this one. Okay, so just now we have done, so we already found the expansion for arc cos x. So C, find this one. So arc cos x, the expansion is like this, right? So just copy in. All right, integrate this one. So next step, integrate. So pi over 2 is a constant. So integrate a constant, you get pi over 2x. This one, x power 1. So index plus 1, so become x squared over 2. X power 3, index plus 1, x power 4 over 4. 1 over 6 is a coefficient, just remain. X power 5 plus 1, x power 6 over 6. 3 over 40 just remain. All right, don't forget your plus dot dot dot. And the limit. All right. So next step, sub 0.5 into each term. All the x becomes 0.5. Minus. All right, so don't forget plus. Then this is the first part. This is for upper limit. Minus, don't forget this one, sub 0 in. But because all the terms is with x, so all the term will become 0. Okay, must write also. Alright, now use your calculator. Okay, approximate sign. So to 3 decimal places. So the answer is 0.658. And then don't forget this one. Remember, don't forget this one. Have to write in bracket 3 decimal places. Okay, now complete the whole question for 2018, which is 15 marks. Okay, I make it bigger so you can see the answer. Okay. Okay. All right. Okay, so we have complete this part for today. We have complete 5.1. No, sorry. Yeah, we have complete 5.1.4.2. All right. So we left one more small part only. 5.1.4.3. Okay. All right. So homework, as usual. All right. So homework. There is, for this part, there is no question in your textbook or no exercise in your textbook. All right. So your homework will be, you go back to the note, your notes, page 10 here. This one. Okay, I have discussed C and D. So your homework will be A, B, and E. All right. Then STPM 2018 repeat paper, question 5, and STPM 2019 repeat paper, question 5. All this will be your homework. All right. After this, please complete your quiz. All right, complete your quiz. I skipped this question. STPM 2017 repeat paper, question 5. Later I snap and forward into the. Later I will snap and forward into the WhatsApp group. Okay, and also STPM 2020 question 5. Okay. I think I will show you here. Okay, this is a question 2017 repeat paper. You see or not? Show that the Maclaurin series for this one is this one. 8 marks. Familiar, right? Yes, it's actually this part exactly same as your 2018. You see, this question came out in 2017 repeat paper. Then in 2018, they asked almost the same thing. See or not? Same function. They want you to show this. They give you 8 marks. So even though they never say, you know that you have to use Maclaurin's theorem. Alright? In 2018, they split it. They ask you to find dy dx first, then ask you to find this one. See? The answer same. What is it? This is the answer that we got just now. See? Same. Okay? So for 2017, actually this part you don't have to do. Alright? You don't have to do this part. Okay, so because just now I have discussed. But I want you to show this. Hence, obtain the Maclaurin series for arc sine. In 2018, they ask you hence to find the Maclaurin series for arc cos, right? In 2017 unit repeat paper, they want arc sine. So you follow exactly the same step like I discussed just now. Just that this question, you use the formula for differentiate arc cos. This one, you use the formula for differentiate arc sine. Okay, so 2017, this question, you don't have to do the first part. I just want you to do the second part. Alright? And 2020, of course, is the full question or whole question. All right, so question SCPM 2020, I have photoset to you. Okay, you can complete this. So please complete these two quiz and upload into your folder, your Google Drive. All right, upload into your Google Drive by now is around 3, 4, 5. Okay, by 9 o'clock tonight. All right. Excuse me. By 9 o'clock tonight, everyone must forward the answer for the quiz into your Google Drive. Excuse me. And those who haven't sent me the correction for video 4 and video 5, please do it. Okay? All right. Thank you, class.